very less dense. We talk about that black holes are very dense. So how exactly do scientists find out that?
It all like that can be done through what kind of light they emit, what kind of like things orbit them. Like for example, we know that the sun is heavier than all of the planets because combined, because uh, they because everything revolves around the sun. We know Jupiter is heavier. Like we knew that Jupiter was much heavier than Earth way in when Jupiter was discovered, and that was because we knew that it had so many other moons, and a lot of other asteroids can be is sucked on by Jupiter. So it depends on what kind of thing that you are observing. Like for example, your star planets, you can observe how heavy they are through the kind of mass they have, like how big they are. And how big they are, they kind of depend on usually they're like for exoplanets, the size of the planet is calculated by the transit. So basically, when a planet comes in front of its host star, it dims the light of the star. So how much does it dim it? That From that information, you can find out how large the planet is and how far the planet is. So there are different methods for black holes. You again see what's around that black hole, how much light, what's the accretion disk like, how much light's it emitting, what kind of things are rotating around it, how its movement is like. And again, and from mathematics, and from that you can calculate how big is the event horizon. We'll talk about event horizon today. How big is the event horizon? And once you know how big the event horizon is, you'll find you'll know how massive it is.
Yeah.
Similarly, for neutron stars or white dwarfs, again, the smaller the neutron star or white dwarf is, the heavier it is. We'll talk about why it's the case and why it's not the opposite. So there are different methods. There's no one method where they can identify how heavy they are and stuff.
Ayan, I get to your question. It comes to the fact that nobody has actually gone to any other planet, to Jupiter, and measured its mass or something like that. So all these measurements are made indirectly. We have a number of indirect ways of measuring the various parameters of planets and other celestial objects. When it comes to mass, the easiest one is of course by measuring we can study its gravity. Gravity will give us the idea about the mass. All right, and there are very simple techniques right from parallax method. When you come to grade 11, we'll study a little bit more about this, that we can find out its radius, we can calculate its volume because they're practically spherical in shape. Then we have an idea about density. And even in the last class that Pantho was talking of, we have absorption and emission spectrums. They also help us know a lot about the composition of the celestial objects. I hope you've got a little clarity after what Pantho has explained and what I'm trying to explain.
Yes, ma'am.
Okay, chalo,
Uh,
Pantho, take it forward with
yeah.
it now.
Is my screen visible?
It is, yeah.
Okay, good. So we'll quickly discuss the last quiz. So the universe is 13.7 million years old. Uh, Anybody would like to answer? Well, it's written as false.
False.
Yeah. So how much old is it?
13.77 billion millimeter.
No,
Billion.
it's billion. Like 13.7 is not the problem. It says million years, and the actual age is in billion
Yeah,
years. Yeah,
I had confused it.
it's okay. It's okay. So deuterium nucleus contains. Okay. Also, there was a mistake. It was supposed to be multi-correct. We mistakenly made a single correct. So what the answer would be? All of you will get marks for this. But what is the answer? Wait.
Is it both?
Okay, sorry. It has both. Okay, there was somewhere else. Okay, no, isotope question. Okay, it's both. Helium-3 is an isotope of helium-4. True or false?
True.
Yeah. Isotopes have the same number of.
New proton.
Protons.
Yeah. What is the main factors used to categorize stars?
Mass and temperature.
Mass and temperature.
mass
Yeah.
and temperature.
Perfect. Then what is the last element formed during fusion in a dying star?
Iron.
Iron.
Okay, good. So now I think we'll start with the next session. If you guys have any question, feel free to ask. Let me share my screen. My screen is visible, right?
Yes, it just started.
Okay.
Yes.
Okay. Okay. So first thing, the thing that I wanted to address last time, but we did not have time. That is, why is the iron nucleus stable? You also had questions regarding this. So for smaller elements before iron, basically, the nucleus is small and does not have a lot of nucleons, that is protons and neutrons. So if we add more nucleons to it, they're more likely to stick together due to the strong force, because in larger distances, the strong force is attractive, right? And thus they can fuse to attain more stability of the nucleus. For heavier elements, after iron, the nucleus is big and has a lot of nucleons. So the particles at one side, in that whole nucleus, at one side, they don't feel much strong forces from the other side, because at very huge nucleuses, the ranges die down. So from the other end, that particle does not attract the last particle with its strong nuclear force. So it does not have that much attraction, but the electromagnetic force still repels these protons from each other, and that's why these nucleuses are unstable, and they like to break apart into smaller, more stable nucleuses, and that's why they perform fission to attain more stability. Iron falls in the middle of this, and so both fusion and fission create less stable outcomes. Any questions?
I'm sorry, I did not understand why is the iron nucleus more stable?
Okay, so in the nucleus, there you have protons and neutrons, right? They are combinedly called nucleons. So the atoms, the elements before iron, that is your hydrogen, helium, lithium, till silicon, oxygen, they are all before iron. So they have they have a very less number of nucleons, because obviously they are less heavier elements. So, and as you know, that the strong force is attractive at larger distances. So if another similar smaller nucleon collides with it, it is more likely to stick together due to the strong force, because it's attractive. It does not have a lot of protons, so it does not have a lot of magnitude of repulsion, which because of the electromagnetic force, and thus it can stick together due to the attraction of the strong force, and that's why they fuse together to form more stable nucleuses. Did you understand this?
Yes.
Okay, so similarly for heavier elements, now these elements have a lot of neutrons and protons, like for example gold, uranium, they have a lot. So in 30s 40, like in fact the most recent, like right now we have the heaviest element that we have, it has 118 protons. So all of these, so it has a lot of protons. So more the number of protons, the more it has repulsion due to the electromagnetic force, and because of that it also has a lot of neutrons, and for that the whole nucleus becomes very big. And because the strong force is have a range, and after that range it cannot reciprocate, it can't attract. Usually at one point we'll find where one end of the one end of the nucleus, the particle here, will not be able to exert its attraction from the particle here. So, and in between there are a lot of nucleons, but the repulsion would still be able to the nucleons will still be able to repel each other, and that's why it has more tendency to repel and disintegrate into smaller nucleuses. and that's why fission happens. Like we all know that nuclear fission, like uranium breaks down, and like it performs nuclear fission. So that's because the molecule, that nucleus is unstable. The repulsion is much more stronger than the attraction of the strong force, and that's why it breaks down. So that's why the heavier elements are not stable. So iron is basically falls in the middle of this. So both fusion and fission, they create less stable outcomes, because once, like if it fuses, then it will form heavier elements with higher nucleons, higher number of nucleons, which again will be in the heavier elements, and they'll repel each other, and they'll perform fission to come back to iron. Similarly, if iron performs fission, it will break down into smaller nucleuses. Like for example, oxygen and carbon. Now they have a tendency to fuse again to form iron. So that's why iron is in the equilibrium. So iron doesn't fuse or performs fission. Okay.
Yes, thank you.
Okay, so now we come to the life cycle of a star. So initially we have something called a stellar nebula. It basically where the stars are formed. We talked about this last class. So from a stellar nebula, either an average mass star, or a massive star can be formed. These massive and these stars, then at the end of their life cycle, they turn into red giant, average star, and for massive star, they become red supergiants. The size is not up to scale. Last time we talked about why it becomes a red giant, right? So after that, if it's a red giant, it then the outer layer, they just like diffuse out, and you get a white dwarf. In red supergiants, the whole star collapses and it explodes, which is a supernova, and it gives you a neutron star or a black hole depending on the mass. Cool.
Yeah.
Okay, so
Yes.
next we'll see that the simulation of death of our own sun.
The volume is very low.
Yeah.
The volume is very low.
Okay.
We are not able to hear the video. We can see it, but we can't hear it.
Oh. Wait, I think I'll then I guess I'll stop sharing and share again. Can you hear it now?
It is louder, but it's still not clear.
It's not audible, Panthu. Maybe if you can open it in the YouTube and share via the.
Yes, I'll try that. I don't know what's wrong.
Never mind.
Is it visible? Is it audible now?
Yes.
It's audible?
Yes.
Okay, cool.
It's not actually.
It's not. Even I can't hear.
It's not now.
Maybe,
No.
maybe Panthu, maybe you can give a bit of commentary along with the video.
Can
Okay,
you
so
put the link in the chat?
You can send
Yeah.
the link in the chat. We'll watch it.
Yeah.
I'll do that for other videos. For this video, you don't really need the audio. You can just watch it because it does not have a. It just has a spooky background noise. So if you want, I can just play this. You understand what it is, and for the other videos, I'll do something like that. Cool.
Okay.
This is basically tells. It's basically your sun's red giant phase. The sun will swell up, and it will engulf the orbits of Mercury, Venus, and most probably also Earth. But for that, there's like a margin of error. But definitely for Mercury and Venus, and it starts pulsating because of the fuel, and it then dissipates into a planetary nebula, leaving a small white dwarf behind. Is it okay?
Yes.
Okay, so now we come to a white dwarf star. So stars with total mass ranging from 0.08 to 8 solar masses, SMA solar masses, leave these behind. Only the core forms the white dwarf. So the mass of the white dwarf ranges from 0.08 to 1.4 solar masses. Now this 1.4 is actually an important thing. We'll discuss this in the next few slides respectively. They're usually a little bigger than the diameter of the Earth. So something as small as the Earth will have a mass of around 1.4 solar masses. So that is dense. So it has a temperature of about 100,000 Kelvin, but can't perform fusion because it does not have the fuel for fusion. It slowly will lose all its light through radiation because it can't fuse more. So all the light it has, all the energy that it has, it will slowly but surely radiate out into space, and it will become a black dwarf, which is basically just a lightless white dwarf. But the estimated time for a white dwarf to become a black dwarf is in the trillions of years. So we can't see any black dwarf as of now. They are hypothetical concepts, but it surely will do something very similar to this. Now they also have a very thin atmosphere of hydrogen and helium. Eh, all the and it still has some bit of like hydrogen, like unused hydrogen, unused helium, and it usually forms a very thin atmosphere. But most of the atmosphere actually they crush into the whole surface, but there still is a very thin atmosphere, and that's only possible for hydrogen and helium because they are the lightest elements. uh, the stars which become white dwarfs live for around 10 billion years. This is important because our sun is also among these stars. So the estimated lifespan of the sun is also 10 billion years. And from that, we have the sun has been alive for over 5 billion years now. So we are literally in the middle of sun's middle age crisis. And after around like 4.6 to like 5 billion years after this, the sun will actually go and become a red giant and then a white dwarf. Any questions?
How did the white dwarfs become black dwarfs?
Okay, so white dwarfs, they have light, right? Like when all the energy, when it became a planetary nebula, everything went away, but it still has energy, right? Because it was crushed, and that created more energy. So it has energy, and usually energy is stored in form of photons, which is basically light. So, and like it has its temperature is around like 100,000 Kelvin, right? So that temperature also becomes like it's also stored as like energy. Your heat equals to energy, and that energy is stored mostly as in photons. And now, like anything that has energy radiates light, like you, me, everyone. But the thing is, our body temperature is so low that most of our light photons that we emit, they fall in the infrared region, and that's why infrared cameras can see through, like, yeah, you might have seen infrared cameras where you can, like, if you're it can see through plastic, clothes, because it reads the temperature, the infrared photons which is given off by anything which has a temperature. Now, because it can't, because in for white dwarf it can't fuse, most of its photons are in the visible spectrum. Most of it, like 100,000 Kelvin, it stores in the visible spectrum, and that's why this is the light that we can see. Now, most of this light will, and because and everything that has a temperature will radiate photons, radiate energy, and that's why these will also, white dwarfs will also radiate energy. It's very slow. Radiation takes a lot of time, but slowly all the photons that is stored inside the white dwarf will escape out into space. It will slowly, slowly the temperature will fall as the photons radiate. The temperature will fall, and eventually it will become the temperature will become similar to the temperature of empty space. And at that moment, that is around 1.2 1.5 Kelvin, and at that point it will have no more photons, no more energy, no more heat energy to radiate, and at that point it will become a black dwarf because it can't radiate any energy, any photons that we can see. Is that
Yes.
okay?
Yes. Thank you.
Okay, so how does the white dwarf exist and doesn't collapse further? It's all thanks to electrons. In a white dwarf, due to pressure, because it's crushed so heavily, the atoms gets overlapped so much that they start sharing electrons. So they flow through the whole star. It has a name. It's called degenerate matter. Usually, no two electrons can. Sorry, it we can. It's a misprint. Can no two electrons can have the same energy level. That's Pauli's exclusion principle. You guys will learn it in your later classes. So now the electrons have to have every position available in the star and every velocity, because your position and velocity, they determine where you are and how much energy you have. So to make sure that all the electrons, which now mostly occupy similar spaces, so that they don't have the same energy, they will actually be have like all the positions available in the star and all the velocities available to a electron. And this diverse the electron movement creates another kind of pressure, which is called the electron degeneracy pressure here, which counters the gravitational force, and that's why it does not collapse further. If the star was massive enough, it can still collapse it further into a neutron star, but we'll get to that later. So white dwarfs can only exist all thanks to electrons. Any questions regarding this? Any questions? Okay, then I guess I'll move ahead. Okay, so now we come to supernova. Heavier the white dwarf, the smaller it will get, but eventually the electron degeneracy pressure cannot counter the gravitational force. It should be forced. The reason why white dwarf gets smaller as they get heavier is because the greater the gravitational force, the more the more pressure electron needs to counter that, and it can only get that much pressure if the electrons move even more faster with greater momentum, greater velocity, and that's only possible if they have less positions to occupy. That's why the white dwarfs get smaller, so that more electrons have to have more diverse velocities, so that they don't have the same energies, because Pauli's exclusion principle cannot be broken. Yeah, any questions? Am I audible?
Yes. I have a question. Then, how long does the whole process of a star going into becoming a black hole or a supernova take?
Usually supernovas, I'll get to that later. Like, so, okay, so for supernovas, it usually become supernova in a fraction of a second. Like once it forms iron, and once all the fuel is done, it forms iron, and most of the core is just iron now. And as soon as the fusion stops, the whole star collapses in fraction of a second, and that creates a lot of, like, due to friction, due to other quantum mechanics, due to like repulsion. That's why they create a lot of energy in one single instant, and that's why all the outer layers, they are blasted off into the universe, and it usually shines around like 100 billion suns, like luminosity of the 100 billion suns. So yeah, it happens instantaneous, but that bright flash usually stays for a few days or weeks. Okay.
Okay, thank you.
Okay, so yeah, where was I? Yeah, the limit was found to be 1.4 solar masses by Subramaniam Chandrasekhar. This is called the Chandrasekhar limit. According to it, if the mass of the core of a star or a white dwarf is more than 1.4 solar mass, it undergoes a supernova. So, any questions regarding this? The whole star does not have to be 1.4 solar masses. Only the core has to be more than 1.4 solar masses.
I have a
After,
question.
yeah, ask.
So it's from the slide before the last one. How do you can you explain the third point, the
Paul's
energy level
exclusion
point?
principle. Okay, so this is a theory. This is a principle in quantum mechanics, and it cannot be broken. So it basically states that all fermions, that is your electrons, your protons, your neutrons, anything which have a plus half or a minus half spin. You remember we talked about spin, right, before this? So anything which has a plus half or a minus half spin is a fermion. And Pauli's exclusion principle states that uh, like no two fermions can have the exact same energy level. It usually applies in atoms. So in an atom, there are a lot of electrons, right? So depending on the atom, there are a different number of electrons. Now, like for example, hydrogen has two electrons, but both electrons need to have different number of energies. No two electron in an atom can have the same amount of energy as the other one. For example, in a hydrogen atom, one like it's in the same shell, it rotates in the same orbit. So the only difference, and with the same speed, so only difference the only different way where it can have a different energy is by their spin. So one electron spins up and the other electron spins down, right? So and that's how the electron orbitals are created. One electron always spins up and one electron always spins down. So but in degenerate matter, your atoms overlap with each other. So like basically the your atoms supposed to have a lot of free spaces between them, right? But when the gravity is strong enough to make a white dwarf, the atoms, they overlap with each other, and because of that they share electrons. And now because they share electrons, your Pauli's exclusion principle goes from just being inside the atom to the whole star, right? And now in that whole star, that whole earth-sized star, the white dwarf, and in that whole star every electron needs to have a different amount of energy. And your energy depends on where the star is and how fast it's moving, right? So if it overlaps, if electrons overlap, if atoms overlap, electrons overlap, the more they overlap, the less positions, the less unique positions it will have, because a lot of electrons will be at the same place at the same time. But that's not possible for Pauli's exclusion principle. So the only way it can have a different energy if it has a different velocity. So that's why you get all like different, or like all kinds of velocity an electron can have. They're all inside that white dwarf, and that's how that. And as the electron is moving, and kinetic energy builds up, and that creates a pressure, and that pressure holds the gravity. Like it stabilizes the gravity, it counters it. Is it better now?
Yeah.
Okay, cool. So now we have another video. This video does normally doesn't have any volume. It basically shows off how a supernova takes place. It's an artist
Uh,
rendition.
I have a question.
Hmm.
If you're not able to observe black holes, black dwarfs, then what helps us comprehend them and what they are like?
Maths. It basically boils down to maths. Scientists, they know, physicists know that anything that has temperature radiates light. We radiates in infrared. Our Earth radiates again in like microwaves. So if anything that has a temperature, anything that has a temperature radiates light, and it is true for everything in the universe. Everything. And that should also apply to the white dwarfs. And because of that, they know that it will radiate its light out, and it has again a finite amount of photons inside it. It has a finite amount of light and a finite amount of light, and that is proportionate to its temperature. That is the heat that it has. So using thermodynamics, they found that it would take, like, obviously a star will radiate, that white dwarf will radiate light, and it will take trillions of years, tens and hundreds of trillions of years, but it certainly will happen. So maybe black dwarfs will be something different than what we are thinking, but there will be certainly something called a black dwarf in the future. At that time, we won't, like, maybe the universe will be very dark, because at one point your stars won't be able to be formed, because like each generation of stars, once a star dies, the matter that is flung into space, which mix and matches, which becomes the new nebula, it now has less number of low hydrogen and helium, and has more carbon, oxygen, and iron and heavier elements. So that's why those stars will become, even like, they'll have more heavier elements and they won't be able to fuse. So eventually your star, like, it will still take around like a few billion, maybe a trillion years, but after that no new stars will be able to form. So that time only white dwarfs and neutron stars and black holes will be able to emit light or any kind of radiation. So black dwarf will be formed when all the light in the universe is extinguished. But we certainly do know that something like black dwarfs will exist. Is it okay? Is it okay?
Yes.
Okay. So I guess we'll watch this video again. It's basically, this is basically a supernova. It happens instantaneously, and all the flying matter that you see outside, that's the outer layers of the star, and it then becomes a new nebula eventually. And the center then either becomes a neutron star or a black hole. Now we go to neutron stars. The gravity is strong enough, like, after a supernova, if the core of the star becomes a neutron star, the gravity is strong enough to smash the protons and electrons to form neutrons, and thus they are called neutron stars. So we do in white dwarf, we saw that the electrons were able to move freely, and that's created the pressure. But now in neutron stars, at one point the electrons cannot move at all, and at that point the electrons, they smash into the protons and they form neutrons. So this becomes a huge ball of just just neutrons. Stars with an initial mass of 8 to 20 solar masses become neutron stars upon their death. So neutron stars are typically the mass of 1.4 to 3 solar masses. So 1.4, we saw that it's the Chandrasekhar limit, and usually a 20 solar mass star has a core which is around 3 solar masses big. So that's the upper limit of a neutron star. Now they usually have a diameter of only 10 kilometers. So think about it, something as big as a 1.4 or maybe 2 solar masses going average, something shrink down into a size which fits in your average city, which is just like, it's like your a smaller city, not even a big city. The diameter of a neutron star is only 10 kilometers, so it's tiny, and all that matter is densely packed in there. So we'll talk about the density of the neutron star. Is it audible though? It's not? Is it audible?
No.
Okay, I'll post
No, sir.
the link. Okay. This is a video. You guys, Madhav, can you speak? Try to speak. I did not realize. If you're speaking right now, then you are not audible. If you can, then please watch that video till I'll try to fix what's wrong.
But Pampu, can we open it in the YouTube and share it?
Like 49 का सिर्फ 9 करना है और 1 का
If you open it in the YouTube separately and then share that tab.
Okay. Wait, I'll try once more. My screen's visible, right?
About once every century.
Hello?
Yeah, perfect now.
It's
It was audible also.
It's
A
audible,
mass-
okay.
About once every century, a massive star somewhere in our galaxy runs out of fuel. This happens after millions of years of heat and pressure have fused the star's hydrogen into heavier elements like helium, carbon, and nitrogen, all the way to iron. No longer able to produce sufficient energy to maintain its structure, it collapses under its own gravitational pressure and explodes in a supernova. The star shoots most of its innards into space, seeding the galaxy with heavy elements. But what this cataclysmic eruption leaves behind might be even more remarkable. A ball of matter so dense that atomic electrons collapse from their quantum orbits into the depths of atomic nuclei. The death of that star is the birth of a neutron star, one of the densest known objects in the universe, and a laboratory for the strange physics of supercondensed matter. But what is a neutron star? Think of a compact ball inside of which protons and electrons fuse into neutrons and form a frictionless liquid called a superfluid, surrounded by a crust. This material is incredibly dense, the equivalent of the mass of a fully loaded container ship squeezed into a human hair. or the mass of Mount Everest in a space of a sugar cube. Deeper in the crust, the neutron superfluid forms different phases that physicists call nuclear pasta, as it's squeezed from lasagna to spaghetti-like shapes. The massive precursors to neutron stars often spin. When they collapse, stars that are typically millions of kilometers wide compress down to neutron stars that are only about 25 kilometers across. But the original star's angular momentum is preserved. So for the same reason that a figure skater's spin accelerates when they bring in their arms, the neutron star spins much more rapidly than its parent. The fastest neutron star on record rotates over 700 times every second, which means that a point on its surface whirls through space at more than a fifth of the speed of light. Neutron stars also have the strongest magnetic field of any known object. This magnetic concentration forms vortexes that radiate beams from the magnetic poles. Since the poles aren't always aligned with the rotational axis of the star, the beams spin like lighthouse beacons, which appear to blink when viewed from Earth. We call those pulsars. The detection of one of these tantalizing flashing signals by astrophysicist Jocelyn Bell in 1967 was in fact the way we indirectly discovered neutron stars in the first place. An aging neutron star's furious rotation slows over a period of billions of years as it radiates away its energy in the form of electromagnetic and gravity waves. But not all neutron stars disappear so quietly. For example, we've observed binary systems where a neutron star co-orbits another star. A neutron star can feed on a lighter companion, gorging on its more loosely bound atmosphere before eventually collapsing cataclysmically into a black hole. While many stars exist as binary systems, only a small percentage of those end up as neutron star binaries, where two neutron stars circle each other in a waltz doomed to end as a merger. When they finally collide, they send gravity waves through space-time like ripples from a stone thrown into a calm lake. Einstein's theory of general relativity predicted this phenomenon over 100 years ago, but it wasn't directly verified until 2017, when gravitational wave observatories LIGO and Virgo observed a neutron star collision. Other telescopes picked up a burst of gamma rays and a flash of light, and later X-rays and radio signals, all from the same impact. That became the most studied event in the history of astronomy. It yielded a treasure trove of data that's helped pin down the speed of gravity, bolster important theories in astrophysics, and provide evidence for the origin of heavy elements like gold and platinum. Neutron stars haven't given up all their secrets yet. LIGO and Virgo are being upgraded to detect more collisions. That'll help us learn what else the spectacular demise of these dense, pulsating, spinning magnets can tell us about the universe. Continue exploring the
Hello. Yeah, I believe you guys would have some questions.
Yes.
Yeah, go on.
I did not understand the part. I do not remember the name clearly, but I think the bit about the liquid forming from the. Yes, I did not understand that bit, how that happens.
Okay, so before this, when I was discussing white dwarf, remember I talked about how electrons they flow, right? They move around the whole star, and that's how it's stable, right? But now you don't have electrons. In fact, in the next slide, I'll be explaining how neutron stars are stable. So right now they don't have electrons to flow, right? but they need to be stable, or otherwise the gravity will again collapse it into a black hole. So in here we come into neutrons. Neutrons flow just like electrons. Now they talked about like the fluid that is formed, that is not viscous at all. Viscosity is basically how thick, well, that's resistance to flow. For example, you might have seen water flows much easily than honey, right? So that is viscosity. Water has a less viscosity. Yeah, water has less viscosity, and honey has more viscosity. And you can basically say viscosity is the friction of fluids. It's basically the same. Your layers of fluid, they rub against each other, and it causes friction, which restricts the motion. But and now one thing to remember, that is, remember I said that all the other forces except the four fundamental forces, all the other forces that we talk about can be explained in terms of the four fundamental forces. Friction is the same. Friction is basically derivative of the electromagnetic force. And like basically when you go to the atomic level, different layers of materials, they'll have electrons, protons, and right, and those electrons and protons, they'll attract the other plate, which will also have like protons and electrons, and that's why it causes friction. Similarly, yeah. So now in neutron stars, you don't have electrons or protons. They're all now fused into neutrons, and neutrons, they don't have any charge. So you take any, even though neutrons have quarks, but you take any combination of quarks, because overall you just have neutrons. You'll always have neutral charged matter, right? There will be no charged matter. There will only be neutral matter, and that's why there is no friction, and that's why the fluid that is formed inside of the moving neutrons is it has zero friction, zero viscosity. Is that okay? Alia, was that okay?
Yes, sorry, I was not able to unmute myself.
Yes, okay. Any other questions?
No.
Any other questions from asking the other people?
I think the video said that they have a strong magnetic field, right? How exactly does that happen if they're made up of neutrons only?
Sorry, yeah. Now the interesting thing is, okay, I'm just like changing it to the next slide. I'm answering your question first. So basically, neutron star, like in the upper layer of neutron star, the surface, the crust of the neutron star, the crust is basically made of white dwarfs matter, because like to form neutrons, to like collapsing electrons and protons into neutrons takes a lot of energy and a lot of force. So uh, the upper layer of the neutron star, it does not have that much pressure from the above, because inside you have you have pressure from the particles above you also, right? But in the surface, there's no such pressures from the above. So the upper layer usually has a lot of electrons and protons. Like they're still not in hydrogen or like that form, but it's mostly like your white dwarf, like similar, like your protons are overlapping, like nucleus are overlapping, and electrons are moving around. You have a lot of white dwarf matter surrounding the non-critical, the non-viscous fluid of the neutrons. And because in the upper layer it has electrons, it has protons, that's why it can have a magnetic field, because that moving particle, that moving electron, it's moving around, right? And now this moving around is those electrons have a much greater velocity than in white dwarfs, and thus it has a much stronger magnetic force than the white dwarfs, because if you remember, then magnetic field is caused by moving charged particle, and it depends on how fast the charged particle is moving. Is it okay?
Is the white dwarf matter you talked about inside the star or is it like outside?
Sorry, I didn't understand. Repeat again.
you said that the white dwarf matter was one of the reasons for the magnetic field. So that's outside the neutron star, right?
Yeah, the crust. Like for example, our Earth has a crust, then a mantle and a core, right? So consider that if our Earth was a neutron star, then the mantle and the core will be your will be your neutron fluid, and the crust will be your white dwarf material, white dwarf matter, or degenerate matter, which is white dwarf matter is called degenerate matter. So it's the crust which has all the protons and neutrons. That's why, and those electrons are moving very fast.
Oh,
Okay. Okay. Any other questions? Okay, so now we come to stability of neutron stars. Just like white dwarfs, the neutron stars are stable due to the Pauli's exclusion principle. Just like the electrons in the previous case, neutrons also cannot have the same energy because their neutrons are also fermions. They also have plus and minus, plus half and minus half spin. So these neutrons need to occupy all position and velocities. Basically the same thing that we talked about in white dwarf. It's just now replace the electrons with neutrons. So you have neutrons whizzing around with no charge. That creates your non-viscous fluid, and it's moving very fast. And that's how the neutron star is stable. Okay, so any questions regarding neutron star now? Okay, I'll move forward then. Next, we have black holes. Stars with total mass of 20 solar masses and above leave these black holes behind. So the mass of a black hole is 3 solar masses and above, because again, the core only forms a black hole, not the entire star. When the gravity of a star is so strong that the neutrons themselves cannot counter the gravity, the star becomes a black hole. One misconception is black holes are not holes, but they're actually normally a spherical balls. But they are so black, they look so black that you just it just looks like a hole, like there's nothing. That's why the name was black holes, but they're actually just spherical balls, just like your neutron star, just like your stars or planets. It's just a spherical ball. Okay, so black holes misconceptions. Black holes suck matter and light in. Things can still orbit around a black hole easily. Like if our sun suddenly becomes a black hole with the same mass, with the mass of the sun, all the planets will revolve around normally, and they won't feel anything different. Any different. The only difference will be like all the planets will freeze to death because black holes don't fuse hydrogen into helium, so they won't provide us heat and light. So it will be a cold world. But if you change the Earth into if you change your sun into a black hole, same mass, nothing will change. So black holes don't suck matter and light into it. Just outside the event horizon, there is a sphere. Event horizon is basically this black part. You can see, right? The boundary of this black thing is the event horizon. So just beyond the event horizon, there's a sphere where light orbits the black hole. That is called the photon sphere, which is 1.5 times the diameter of the event horizon. So basically around this place, you can see a lot of these things there. Yes, obviously it's the accretion disk also. Like for example, in the original black hole picture that we have now, it's the accretion disk, and this light part is actually photons revolving around the black hole. So the gravity of a black hole near the event horizon is so strong that light, which is supposed to always travel in straight lines, will go around the black hole. That's why there's a funny saying that if you try to rotate around, if you enter the photon sphere, you can actually see the back of your head, because the light, the photons from the back of your head will rotate around and come in front of you. So that's why so that's called the photon sphere. Now the size of the event horizon is called the Schwarzschild radius. More massive the black hole, larger is the event horizon. Schwarzschild radius is basically like every object has a Schwarzschild radius. You take any object, and if you can crush it down and make it or like make the radius of that object its Schwarzschild radius or even smaller, that object will become a black hole. You have a Schwarzschild radius for the sun, which is around just like your marbles, your 2 centimeter marbles, like this small. This is the Schwarzschild radius of the sun. For Earth, the Schwarzschild radius is around it's around the diameter of a proton. So if you can crush the Earth into that smaller thing, it will become a black hole. So, but usually you can't do that because there are different, like the atoms. There's a bond energy. There's the atoms which don't like to be close together. There are different forces which counter that. So black holes are only possible when the gravity is huge, like in very massive stars. So yeah, the more massive the star, larger the event horizon. So here's the video regarding the black holes, and after that I'll take questions.
Stars are incredibly massive collections of mostly hydrogen atoms that collapse from enormous gas clouds under their own gravity. In their core, nuclear fusion crushes hydrogen atoms into helium, releasing a tremendous amount of energy. This energy, in the form of radiation, pushes against gravity, maintaining a delicate balance between the two forces. As long as there is fusion in the core, a star remains stable enough. But for stars with way more mass than our own Sun, the heat and pressure at the core allow them to fuse heavier elements until they reach iron. Unlike all the elements that went before, the fusion process that creates iron doesn't generate any energy. Iron builds up at the center of the star until it reaches a critical amount, and the balance between radiation and gravity is suddenly broken. The core collapses. Within a fraction of a second, the star implodes, moving at about a quarter of the speed of light, feeding even more mass into the core. It's at this very moment that all the heavier elements in the universe are created as the star dies in a supernova explosion. This produces either a neutron star, or if the star is massive enough, the entire mass of the core collapses into a black hole. If you looked at a black hole, what you'd really be seeing is the event horizon. Anything that crosses the event horizon needs to be traveling faster than the speed of light to escape. In other words, it's
I'm sorry, my network went for a second.
I think it would be his network that's gone.
Pantha, are you there?
Oh.
Yeah, it's paused, Vidush. I guess Pantha has lost his connection. I'll just find out. Yeah, children, Pantha has left, is basically trying to rejoin. There's some internet issue at his end. So I guess, are you all following, children?
Yes, ma'am.
Yeah,
Yes,
Pantha is
ma'am.
back. Yeah. Yes, Peter Pantha, you may continue with the video.
I'm sorry, my internet stopped working suddenly. I have no idea how or why. One minute, I'm setting up the presentation again. Is my screen visible?
Yes.
Okay, so
Yes.
yeah. So how much did you watch? Like, where should I begin with? Okay, we'll start from the beginning only, I guess.
Stars are incredibly massive collections of mostly hydrogen atoms that collapse from enormous gas clouds under their own gravity. In their core, nuclear fusion crushes hydrogen atoms into helium, releasing a tremendous amount of energy. This energy, in the form of radiation, pushes against gravity, maintaining a delicate balance between the two forces. As long as there is fusion in the core, a star remains stable enough. But for stars with way more mass than our own Sun, the heat and pressure at the core allow them to fuse heavier elements until they reach iron. Unlike all the elements that went before, the fusion process that creates iron doesn't generate any energy. Iron builds up at the center of the star until it reaches a critical amount, and the balance between radiation and gravity is suddenly broken. The core collapses. Within a fraction of a second, the star implodes, moving at about a quarter of the speed of light, feeding even more mass into the core. It's at this very moment that all the heavier elements in the universe are created as the star dies in a supernova explosion. This produces either a neutron star, or if the star is massive enough, the entire mass of the core collapses into a black hole. If you looked at a black hole, what you'd really be seeing is the event horizon. Anything that crosses the event horizon needs to be traveling faster than the speed of light to escape. In other words, it's impossible. So we just see a black sphere reflecting nothing. But if the event horizon is the black part, what is the whole part of the black hole? The singularity. We're not sure what it is exactly. A singularity may be infinitely dense, meaning all its mass is concentrated into a single point in space with no surface or volume, or something completely different. Right now, we just don't know. It's like a dividing by zero error. By the way, black holes do not suck things up like a vacuum cleaner. If we were to swap the Sun for an equally massive black hole, nothing much would change for Earth, except that we would freeze to death, of course. What would happen to you if you fell into a black hole? The experience of time is different around black holes. From the outside, you seem to slow down as you approach the event horizon, so time passes slower for you. At some point, you would appear to freeze in time, slowly turn red, and disappear. While from your perspective, you can watch the rest of the universe in fast forward, kind of like seeing into the future. Right now, we don't know what happens next, but we think it could be one of two things. One, you die a quick death. A black hole curves space so much that once you cross the event horizon, there is only one possible direction. You can take this literally. Inside the event horizon, you can only go in one direction. It's like being in a really tight alley that closes behind you after each step. The mass of a black hole is so concentrated, at some point even tiny distances of a few centimeters would mean that gravity acts with millions of times more force on different parts of your body. Your cells get torn apart as your body stretches more and more until you're a hot stream of plasma, one atom wide. 2. You die a very quick death. Very soon after you cross the event horizon, you would hit a firewall and be terminated in an instant. Neither of these options are particularly pleasant. How soon you would die depends on the mass of the black hole. A smaller black hole would kill you before you even entered its event horizon, while you probably could travel inside a supermassive black hole for quite a while. As a rule of thumb, the further away from the singularity you are, the longer you live. Black holes come in different sizes. There are stellar mass black holes with a few times the mass of the Sun and the diameter of an asteroid. And then there are these supermassive black holes which are found at the heart of every galaxy and have been feeding for billions of years. Currently, the largest supermassive black hole known is S50014 plus 81, 40 billion times the mass of our Sun. It is 236.7 billion kilometers in diameter, which is 47 times the distance from the Sun to Pluto. As powerful as black holes are, they will eventually evaporate through a process called Hawking radiation. To understand how this works, we have to look at empty space. Empty space is not really empty, but filled with virtual particles popping into existence and annihilating each other again. When this happens right on the edge of a black hole, one of the virtual particles will be drawn into the black hole and the other will escape and become a real particle. So the black hole is losing energy. This happens incredibly slowly at first and gets faster as the black hole becomes smaller. When it arrives at the mass of a large asteroid, it's radiating at room temperature. When it has the mass of a mountain, it radiates with about the heat of our Sun, and in the last second of its life, the black hole radiates away with the energy of billions of nuclear bombs in a huge explosion. But this process is incredibly slow. The biggest black holes we know might take up to a googol years to evaporate. This is so long that when the last black hole radiates away, nobody will be around to witness it. The universe will have become uninhabitable long before.
Yes. Any questions?
I have a question
Yeah.
that once a black hole dies, what will happen to the people or maybe the particles or stuff that had got inside it previously?
That's a very interesting question, and there are theories. Nobody knows for sure. That's the black hole information paradox. So, lot of most we don't know exactly, but there are theories. So, one thing says that, like, again, the wormhole theory. One theory states that the information, the particles that the black hole like enters the black hole, comes out in a different universe, a different part through a white hole. But right now we have never seen a confirmation for a white hole. There's that theory. There's a theory that these virtual particles, they carry the energy of the black hole, so the informations are there. But again, nobody knows whether that's true or not. So there are a lot of theories, but nobody knows for sure.
Okay, thank you.
Yes, Vidush.
Um, the video mentioned some when it was talking about Hawking radiation.
Hmm.
In that part, it mentioned particles just appearing, crashing into each other, and I'm not sure what happened after that. But where do these particles appear from? Is this antimatter and matter that crash into each other and release a lot of energy?
You are half right. So basically, virtual particles are particles. They're basically, again, they're particles which have no mass or energy. They just pop in, and always particles have to pop in a pair, because again, particles are only just like disturbances in the field, right? So if again, if you have a rope and you, like, if you play with it, like if you take a rope and just like move it one side, you'll get a wave, right? A wave has a crest, and then it goes down, right? So you get this. So this above thing, that becomes one particle, and this becomes another particle. Now, according to quantum mechanics, there's the Heisenberg uncertainty principle, which says that position and momentum, or energy and time, like these two things, they cannot be zero. Like, there's always uncertainty about this. So you can't. So for a particle, for a subatomic particle, you can't say exactly where it is or exactly how fast it's moving, because then the uncertainty of the other thing becomes infinite. So if there's a particle and you know where it is, if you somehow identify that, yes, here is the particle, and with 100% accuracy, then you will have no information about its momentum or velocity. Similarly, so there's always some uncertainties regarding a pair of factors. So and that also is true for, and then that's why actually why in quantum mechanics a lot of particles and things are seen as probabilistically, because there's a probability that the electron is here. There's a larger probability that it's here, the other, but far enough the probability is less, but that does not mean that it's zero. Similarly, energy and time also have a similar like a similar relationship. So in a space, in a given time, you can't be sure that the energy is zero. Energy can't be zero. There will be a very small bumps of energy, and and free space always has fields, right? We talked about fields, and any kind of those quantum fluctuations creates virtual particles. These particles are again virtual because they come into existence. They don't have any real matter or real energy. It's all fluctuation, probabilistic fluctuations. So they come into existence and annihilate each other because there's always one crest, one trough, or one matter, one antimatter, or anything that there is. Now, and that happens everywhere. In fact, in near black hole, the black hole basically stretches space-time in such a way that the fields get excited more than usual. So that's why there are even more particles. There are even more virtual particles. So at the event horizon, yeah, like just at the event horizon, if the virtual particles are coming, one virtual particle will arise inside the event horizon and one outside. Now, the more massive the black hole is, the bigger the event horizon is, this virtual radius is, more is the likely that both the particles will go inside the event horizon, because there is very less difference of energy. But there is a small possibility, very tiny possibility, that the virtual particle, which is outside the event horizon, will go out, like will go the opposite direction of the black hole. Then that virtual particle needs energy, right, to become a real particle. It takes the energy from the black hole out. There's a very tiny loss of energy happening every single time. Now, the smaller the event horizon becomes, the more the chances of the virtual particle outside the event horizon, to escape and not fall into the black hole. And they all take a tiny bit of energy with them. And that's basically the basics of Hawking radiation. Is it okay?
Okay.
Yeah. Any other questions? No questions overall. This is the last slide for today. So we have covered everything that we wanted to. Now then, I'll give you the quiz for this time, this session, and you can submit it and then you can leave.
I have a question, but it's not related to what we did just now.
Okay, ask.
Yes. My